So let's go back to our coin toss experiment, right? So basically, what we are doing is we are just tossing a coin, and we are saying that okay, if it can land on heads or it can land on tails, right? So what we are doing is that we are representing you know this heads as, let's say, 1, or tails as 0, right? So, okay, this is not the probability of heads. This is just representing heads as 1 and tails as 0. So I'm trying to, generalize this idea that you're doing an experiment and you have basically two outcomes, right? So it could be anything, right? So, coin toss is, yeah, tossing a coin is just uh, one example of it, but it could be anything. You're like playing a game, and the output could be you win the game or you lose the game, right? So, and so on. What I'm trying to say is that in any experiment where your outcome is binary, you can represent it as 1 or 0. So I'm taking the example of coin toss. So I'm saying that, okay, I can represent heads as 1 and tails as 0. So let's say, you represent the outcome with the random variable x, and you are saying that probability that x equals to 1. In other way, you can say that probability that the coin lands on heads, that equals to p. Okay. So this is not 50-50. Like, the probability is not half, because it might not be a unbiased coin, right? The coin is biased. So p could be any value between 0 and 1, both inclusive, right? So it's a biased coin. So such that the probability of it landing on heads is uh, could be more or less than probability of landing on tails. Okay? And the probability of landing on tails, that is probability x equals to 0, would be basically 1 minus p, right? So let's say that I represent x as, okay, this is called the Bernoulli distribution. Okay. So what happens is that uh, so what is the probability of x? How do you represent the probability? So it is p uh, to the power of, let's say, xi times 1. I'll explain this in a bit. Okay. Okay. So you see, this experiment has probability that the x will take value 1 with p. Okay, the probability that x will take value 1 is p, and the probability that x will take value 0 is 1 minus p, right? So if uh, x takes value 1, so this expression becomes p to the power of 1, and this 1 minus p to the power 0. So that is basically p, right? And if x takes value 0, then this will turn out to be 1 minus p. So this is what is representation of this experiment, right? Is that clear? And here we can add one indicator function where we can say that, okay, xi takes values between 0 and 1. Okay, values not in between, but only discrete values 0 and 1, right? So in case x takes value 0, then we will have probability p, and x takes values 1, we'll get probability 1 minus p. Is that clear? Right? So this is just a Bernoulli trial that I am trying to say. Okay. Now you can repeat this experiment, 100 times, or let's say n times. So then what will be the probability that, of all the variables x1, x2 till xn, let's say. You repeat this experiment n times, then what will be the probability distribution? Considering, again, here the multiplication will again come in. So considering that each of the trials are independent, we will say that, okay, this is equal to p of x1 times p of x2 times dot 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 till p of xn. And each of this will have this distribution. So this will be a product. So this is the product sign of I equals to 1 to n. and P of xi times 1 minus P times 1 minus xi. Okay. And with the indicator function, I can indicate that, xi takes value 0 and 1, right?